Hello, everyone, and thank you for coming. So my name is Riccardo, and I will talk about FRP as Functional Reactive Programming for Natural User Interface. So because time constrained, the original talk was like 2 hours and something. So I will focus in the main topic, which is FRP. The natural interface will be touched anyways. I'm going to use LeapMotion. I'm going to describe what it is in a couple slides. And I'm going to have a code sample using this device, and I will introduce a little bit here. However, all the material, GitHub, the complete full slide, and code sample on GitHub, if you want to go further down and check the rest of the material. So this presentation really a journey, my experience that I had building not one but few libraries implementing functionality programming in F#. So before start, any Haskell programmer here? All right, that's good actually. So I'm gonna see coming, the idea actually comes from the Haskell world, right? And I get all my research from that side, and I brought it into F#. So the agenda, we're gonna cover of course, what it is, and I will talk about the difference between reactive programming and functionality programming. There is a bit of confusion between these two terms. The foundation motivation behind functionality programming, and then we're going to cover two different implementations, right? One from the original paper, and one from the more modern paper of FRP, and then it's going to be more clear in the following slides. So the idea will cover, try to keep the presentation like 50% theoretical, okay, and then jump in the code and see some code sample. This is the boring slide about me. I'm originally from Italy, but I spent the last 10 years in the US, where I run the local F# user group. Recently, I switched company working for StatMuse as a startup in San Francisco. We do sport statistic analysis, provide some natural language interfaces, all in F#. And currently, I'm authoring a book about how apply functional programming for building scalable application. And yes, I do love pugs. So just to give you a high level before start the main topic, we're going to use Leap for the code sample, but it's going to be the last part. And Leap, anybody familiar with Leap? Motion? Okay, cool. Oh, a few of you. Good. It's a 3D motion device, right? It uses a Cartesian coordinate plan with X, Y, and Z, right? And is able to detect up to 100 frames per second. And it really uses a simple model that detect the movement of your hand, your fingertip, your velocity, your stability, and send up to a controller a series of the frame through an event, right? You just handle the event. And with that, you can actually apply some logic to detect some gesture like swipe, or circle, and so on. So it's a pretty cool device. It's not super expensive. I think it's like $60, $70. It's a nice toy to have. And the code and the game we're going to play with, I will play, but you can come after the talk, is the paddle game. That the inspiration comes from the Haskell School Expression book, which is a pretty nice, simple read. It's like 240 pages. It's a nice book. I recommend it. But what is interesting about this book, and there is one chapter that cover the functional reactive animation, right? And this chapter is a talk about how implement FRP, and they build this game, and they claim, actually, they build it in 20 lines of code. So I was able to implement it using the library in F#. And any guess, many lines? 37. I know, but we don't have type classes in F#, right? Anyway, so let's start with functionality programming, right? So what is functionality programming? And this is not really an easy answer, because there are two sides of the spectrum, right? We have an academic part of the industry with, I'm going to tell you that FRP is values that change over time, And then there is another side of the industry that is going to tell you that functionality programming is really like an umbrella, a set of different kind of terms, right? And definition. And the problem is that if you think about it, here we have 3 words, right? But if you combine these 3 words, you have different kind of meaning, right? We have functional programming first, right? And I know that this kind of audience probably kind of silly give a definition, but it's a paradigm that treats computation as evaluation expression and try to avoid the mutational state, and also have very important properties, such as composition, which is my favorite, and declarative style, and so on. But then you play again with these 3 words, and you get reactive programming, right? So, and reactive really mean responsive to stimulus, but these days become really ubiquitous, right? If you build any kind of application where you need a real-time component, you are exposed to reactive techniques, right? And this has been a lot of confusion between people because they think that if you can apply high-order operation against event, such as filter, map, or reduce, you're doing functionality programming. And this is not true. However, there is a very close relation between reactive programming and functional programming due to the fact that reactive programming use functional constructor to achieve composable event abstraction. So this is a F#, briefly. This is event combinators, right? You just combine and compose event combinators to apply high-order operation against event. You use the pipe operator just to chain as a series operation, right? So this is reactive programming. But then we have all the 3 words put together, which is the topic of today. And this is a talk about a paper of Connor Elliott and Paul Hudaki that wrote 20 years ago. And it's about composable dynamically evolving values over time, right? Which means you get values that vary over time, avoid the mutational state. Really, the idea of functionality programming is integrate time flow and compositional event in functional programming. So this is the original paper of FRP that was written in '97, and which described the first implementation, right, of functionality programming. And they used Haskell and used to implement Fran as functional reactive animation, a library to interact with 2-dimensional and 3-dimensional images, right? And Fran is based on a notion of 2 polymorphic data types that are behaviors and event that we'll cover very well in the coming slides. And they cover the value they change in continuous and discrete times. And these concepts are still used today in modern implementation. By the way, if you have any questions, just yell at me. I'm here. I'll be happy to answer. So this is some of the domain where functional reactive programming inspired or already being used, right? And really, the idea of functionality programming is provide this way to express computation and avoid, the complexity compared to traditional way. So you can see, the relation toward the graphical user interface, the front end, right? And lately, it's been heavily utilized in virtual reality and games. And it's becoming mainstream, right? It evolved really in different kind of direction these days. And with different kind of implementation. But you can see again how this is, Bacon.js, React.js, or Angular, and so on. All they have their own implementation of FRP. Anybody familiar with this library, I guess, right? I mean, at least you heard about it. But again, you can see how very there is this relation of FRP with the front end, or anyways, UI programming. To me, the more interesting is Helm, because different to the other, it's not really, it's a framework, right? But what it does is provide a new language to make FRP more digestible to programmers, right? So what is FRP? So it is a paradigm for building a reactive system, right? And provide this composable abstraction for dynamics values. And this value have a very precise denotational semantic. And we covered the notational semantic, I guess, in one slide or two. But it's a very simple concept. Right? It's a mathematical model. And, but the idea really is used in FRP, or should be used anyways, to build a very elegant vocabulary around your APIs. So there are two main ideas that shape FRP, right? One, I think you cannot see it probably. Ooh. All right, is the denotative, which means that they use a precise compositional semantic and really specify the meaning of each time and build the block. And then we have the temporal continuous, which focus more on the compositional aspect of FRP, right? And it describe how compose in this building block. So the notational semantic, right, is a mathematical expression of the formal meaning of your program or your programming language, right? Is like, for instance, it provides a mathematical interpretation for your program construct, right? So, for instance, when you can use math to prove the correctness of your program. And so, for instance, the notational semantic is no interest to express the meaning of your program, showing what the program does when it runs, right? But really, it tries to convert your program from your native language to a more mathematical expression, right? To a more mathematical representation. So in this slide here, we have a Haskell, right? Which is a language of very strong denotational semantic. And you can see here we have an expression, right? 1 to n, which is pretty clear what it does. Get all the number 1 to n. And then with the product, which is pretty clear, right? Is a function that calculates the product of the expression 1 to n. So this is a factorial function. It's pretty clear the intention, right? It is a factorial function from a math text. Well, this is the same, right? Written in C, right? So it's quite clear which of the two languages have a strong denotational semantic. And what is important about denotational semantic is the compositional aspect, right? Is how you can compose and construct the different denotational parts of your program. So the benefit and motivation really it fit quite well in FRP. And Connor Elliott has a very strong opinion regarding denotational semantic in this paper. And really, as I mentioned earlier, is a great mechanism for building an elegant vocabulary around your API. But mostly, really, what he mentioned in his paper, the notational semantic lead to simple design, right? And with that, simple design are easier to reason about, right? And allowed us to provide us the opportunity to reason in further down and more deeply to build a more complete and elaborated library API. So really, the goal here are an elegant semantic, but also reusable abstraction. Bless you. All right, so let's start finally to build our domain, right? So FRP is implemented by different data types. And the first one is the time, which is cover the domain of the real numbers, which in F# is float. So, and the reason the choice of continuous time is because provide a more composable and modular programming model, right? Compared with the one they use discrete time. And I'm going to cover discrete and continuous time in the next slide briefly. But really, modularity is about modeling, right? And FRP achieve modeling through continuous time. So I talk about a bit continuous time, discrete time. So just give a definition of 3 different time here, right, to clarify the confusion. Well, continuous time, well, think about your clock, right? You check now your clock, you get a value. And you take a look later on, you get a different value. Because always the time continues to flow under the scene, right? Discrete time, well, that's pretty clear, right? It's like, think about the mouse, right? Continuous time is the motion, the mouse continues to move. But when you click the mouse, it's discrete, right? So you know when this happens, just according to when the user clicks the mouse. And then we have virtual time. This is more interesting because virtual time is used by libraries such as reactive extension or other more reactive programming libraries. And virtual time, really, the idea can switch the concurrency model at any time of the computation to run high-order operation regardless the time aspect, right? Which means that you can rerun historical data and rerun or other, high-order operation regardless if the timestamp is 10 years ago, you can run it today. Any questions so far? All right, and that brings us to probably the most important block, right? So this is the central data types of FRP, which is behavior. And sometimes it's called signal, right, in modern implementation. Like Elm it's not true behavior, but sort of. And behavior is a polymorphic data type which evolves, over time, which means that at every single time you get a different values, right? So semantically, behavior is just a function from time to value. And as I mentioned, like the mouse movement, the motion is continuous, right? That's so. Well, we have an example later. So with these simple types, now we can define already a few functions, right? We have the time behavior, which is time to time, which is the identity function, okay? Then we have the behavior that always returns the same value, which is a constant behavior. And then we have a behavior that increase of, this is a typo 2.5, well, it's an increase of 7.5 the speed, right? And this is nice because now I can describe or the speed on an object with a function. So this is and I can build my first implementation of my API. And actually this comes from the idea of the first original paper, right? And I have my first F# library is implemented using this idea. We're gonna cover later in the code sample. And but with this API, I can also rewrite my function, right? So I can use the lift1 just to rewrite, the function that increase the speed 7.5, right? So the lift function is just, take a value and just, lift in a new word, just bring in a box the behavior type. But so behavior are continuous, right? But sometimes behavior needs something, right? We need something to react to behavior. So we need something to react so behavior can change, can be created or can be updated, right? So that's why we need event. An event is a polymorphic type that can have a value or not, and it is discrete. And is represented as a time-ordered sequence of time value pairs. And the time is monotonically not decreasing because, of course, the time is continuous, right? So for each value, there is a specific timestamp, right, which represent the time when the event occurs. And here I just can represent an event that, like, for instance, fire after 3 seconds and increase the time of 2.5, the speed of 2.5. So briefly here, how can I wait by time here? Okay, so super fast here, and think about the mouse, right? So if I want to check if the mouse is inside a rectangle, right? With a classic event view, the event are represented as a discrete. The position are represented as a discrete, right, event, which is not really true FRP. It should be continuous. So with the true FRP, the position is a behavior. So my mouse position is a function time to position, okay, in this case. So I create a in rectangle, which is a two-state behavior, true or false, passing two arguments, which is the two extreme of a rectangle, and that I check the current position. You see I use the parenthesis because I sample the behavior to get the current position and return true or false the state of the mouse inside. So keep in mind how this is implemented, because then we're going to see how you're going to re-implement it using the more modern implementation. All right, so the cool part to me is that there is this association of behavior of value in time, right? So here, the mouse, the move, is not the classic representation of the coordinate x and y. It's really a function of time to value, right? So I have to sample that. And the circle here just when you click the mouse, and this is just discrete. All right, this is so cool, right? So, but how you implement it yourself? Because now we discuss a bit about the theory, right? But so, according with Colin Elliott, I'll put the link there, and you can check online. He answered a Stack Overflow answer. He said, FRP is so easy you can implement it yourself. Well, sort of, right? I mean, to me, I get involved in FRP, and I get more and more excited the more I make my research about FRP. To me, it's a very fascinating topic, right? So we have beautiful semantic, we have behavior, the really time to function time to value. You can express program, with equation reasoning and with event, but still, it's not simple. So to summarize pretty much what we saw so far and how we answer this Stack Overflow question, these are the 4 main points to implement, the FRP, which is, temporal modeling, which is the behavior aspect, which is first class. Then we have event, which cover the discrete side and our first class value. The declarative reactivity, it covers the fact that behavior are expressed in term or reaction to event, right? Because behavior can change or update according to some event. And the polymorphic media, we're going to see later, are just all the set of combinators that you can use to combine these two data types. So great, but it wasn't until I read this paper probably for my 4th time, right? And this is one of my favorite papers because I associate it with good memories. I have my Eureka time, right? When you read a paper and actually finally you get it, you feel smart for once. So I was struggling implementing my first library, and then I was reading this paper, and actually it pretty much was telling me the answer or how to overcome my problems, right? So this paper, this is the link, and I recommend is a nice read. It covers how to re-implement the old paper from a more modern perspective, right? Introduce concepts that weren't there originally in 97, like monad and applicative functors. But what really opened my mind and really made me understand was the fact how we was able to revert from the pulling to the pushing, right? Because the first original paper, to get the value from a behavior, I had to ask for it, right? To sample. But there are some problem with that, right? Think about if the behavior are constant, why should you ask for the same value over time? Or maybe if a behavior depends upon some event, and the event didn't fire, didn't happen, why you to ask for the same value, right? So anyways, he was able to revert from pulling to pushing that I think everybody knows is way better, the reactivity. So this is the new behavior data types, the modern one, which have the notion of reactive values, right? It really decompose the behavior in 2 components, right? Which is reactive values, which are independent of time, and then we have the time function, which are dependent on event. So we have reactive values and non-reactive time function. So really the idea here is considering behavior as a chain of phases, right? Because now you can see the behavior is calling itself, right? And every time an event happens, a new behavior phase materializes, right? So maybe a new behavior is created or a behavior is updated. And these phases are themselves phases, right? So really, the idea really is that behavior is followed by the new behavior, right? With the time when you make the change. So this is the cool part, right? We have the two functions, like the identity function at the time to time, or the pure function. But the cool part here, look at that. This is the F# keyword rec when you have a recursive function, right? Well, why is that? Because if you see now, with the reactivity aspect of the behavior, now the behavior pretty much will call himself and update himself, right? I'm not sure if this is correct. It works, but it's still work in progress. So the first library was for a real project that is working. I left the company now, but nobody called me. This is a more proof of concept, the second library, but it seems working too. But this is more like an interpretation. So as I mentioned now, with the modern implementation that was written in 2007, now we can compose behavior and create a different kind of API. So now behavior are applicative, right? So we have the pure function. Just take a behavior and bring in a behavior word. And then, so we can leverage the fact that what we already know about applicative, right? With all the laws and the specification that come with that. So if you remember, this is the same function when I calculate the position of the mouse inside the rectangle. Now we can rewrite the same using this different API. And the most important function is the apply operator, right? Which applies a time-varying function to a time-varying value at each point in time, right? I think this is pretty cool. Event. This is the event API. You're going to see in the code sample, but event that never happened. The second one is an infix operator, but just a merge. Take two events of the same type, return the event. And other few operator there. This is still come from interpretation of the push and pull paper, right? This is I'm going to try to go quick into the next two slides and then jump in the code. This is the behavior. The only one that I want to point out here that I think is the more useful is the accumulator, because sometimes we're going to see most of our operation system of libraries provide event as so discrete event instead as continuous time, something like position, right? That should be behavior. So there's a trick sometimes use accumulator. They take an initial value, right, and an event and produce a behavior. Now the event is really become a producer, right? So and it keep updating the value of the behavior. So sometimes use this trick to convert an event to a behavior. The switch operator, and also this is interesting because it takes a behavior and an event with a behavior, right? So you start with a state, okay? And when the event fire happen, you switch behavior. But now the cool part is that you can use it recursively, right? You keep switching between behavior. Okay, now let's talk about code, right? Any question about this part? All right, so let's jump in the code. So I have, what time is finished here? 3, 4? Oh, sorry? 4:45, so I have 15 minutes? Okay. All right, so I'm going to run through the first implementation, which is the boring one. So we're going to spend no more than 2 minutes. So I did 2 code samples. One, the boring one, which is the bank account, because I don't want to spend more time there. We choose the first implementation, and then I'm going to play with the game. So the idea here, the bank account, you create the event, and we can have a deposit and get some cash, a withdraw, and you can merge the 2 events using the merge operator, right? Merge the 2 events together. Now, this is the example you can use the accumulator, right? So I have the event, you have initial value, which is the initial balance, which is passed in the constructor here, going to be 0, and pass my function that keep updating the initial value for the value that are coming, right? In F#, everything is a function. So if I put the plus in parentheses, is a function, but this is the same that write, fun b equal, function plus b. It works the same, okay? Oh yeah. I have to put it. And now you can see here as the first implementation, when I change my balance account, I have to sample, right, the new value. And the trick here, I just pass, using the send function, a new value to the event, and when I get some cash, I just pass the event, the amount with a negative value. Pretty simple. So again, this is nothing sexy. I just have some value here. I just run it, so just to prove it that it works. Right? You start with some initial value 10, put $100, take some money out, and this is all happen underneath using event and behavior, which are implemented in this library. Now, this is the library that is work in production, I'm thinking. But so this was built the first time to interrupt with an imperative language. So the behavior follows the same signature, but is passed through a constructor, which means that the majority of the function here belong to the instance of the constructor. Like for instance, the map function here belong to the instance of construction. And here the signature, you can see A to B and return behavior B, where the behavior A is actually the current object. However, in F#, I can create a module to extract all this function and expose it in a more functional manner, right? I'm not going to go into detail how this library is implemented. Download the code and play. This is, it's probably like 400 lines of code. But let's go to the game engine, right? So let's run the code here. So, okay. So as I mentioned, use LeapMotion here. This comes from the inspiration of the ASCO school expression book. And the idea here is that it's all a behavior and event. So we have the ball actually that travel with a velocity and direction, which are behavior, never change until some event happen, maybe a collision, right? Hit the wall, or hit the paddle. Now, even the game as a state, right, which is now is game on. But it can happen that, if the ball doesn't hit the paddle, well, the state of the game also change, the behavior switch, and it's game over, right? So how this is implemented? This follow more the rule of the first implementation, right? So I define my type here using the reactivity version, right? We have behavior, and we have event. But the cool part, how this is implemented, I'm going to go over LeapMotion later here. I'm going to go here. Is this part here. The idea really where, to me, FRP really come is super powerful, that you really build all your behavior, right? That represent your domain, your game, right? The behavior of the ball, that the velocity or the position, and then the event that can change the speed, and then you just compose them together, right? So for instance, you start with the condition position, right? Which is a predicate behavior that check if the ball right now is between +1, -1, which are the two wall of my window game, okay? And if it's inside, it's true. Condition Y, the same. This is more tricky because I had to cover also the bottom one, because that's where the game over behavior happen, right? Now, I put the signature here in the comment, just to be clear. But, so the conditional game over here is a behavior. They take a float and return a Boolean, right? Well, when the position Y of my ball is -1, right, is switch the behavior to false, which means it's game over. So I start to build all these components, all the block, and then in the end, I'm going to compose them together. The LeapMotion, well, this is just a class that, a function that I use to get the current position of my LeapMotion, right? My hand. Briefly, I think they're here. So you have two parts that you write to against LeapMotion. One is the controller, which handle pretty much all the event, and then the listener, which is the one that you build to handle the event. Now, for the listener, the more important event, there are several, but is an on frame, right? Which happen when it detects on frame, like a movement. The problem with with on frame and the Leap is not thread safe. I don't know why they build this way, but if you handle like 100 frames per second, you need to be careful, right? So the good thing about F#, I can leverage, some primitive built-in language like the agent, right? So I can, every time there is an event on the frame receive, I can push my frame to my agent. I can send here, do some calculation. In this case, I just remove the Y and Z because I just need X, left and right movement. And keep recursively the state of my calculation, right? So every time that I need a value, I'm going to ask my agent with a get. Oh my God, this doesn't play well. Doesn't that bother you that in Windows is up, down, the trackball, and in Mac is... so use the get message to the agent to get the last calculation you have, right? You always keep the last calculation. So you have thread safety, and every time you ask for a value, you get always the latest that you need. And here is exposed, like with the LeapMotion function. Pretty simple. So this is where I was telling you about the bad approach and good approach, right? The bad approach is that, unfortunately, even LeapMotion, it gives you the frame and the position as discrete, right? Instead, it should be like continuous over time. So a trick is to create your event and then use the accumulator with the initial value that return a behavior, right? And the event just keep producing new value, updating the behavior. A better approach with the activity implementation behavior, you can just pass the value of the Leap position and recursively call itself. It just updates itself. Okay, now I have the behavior. I can build the behavior of my LeapMotion position, which I have to make the trick because now I have the X coordinate, which is a point, right? I just have to add the size of my paddle, which I just use the apply operator to compose the two behavior. And that's it. Now I start to build the rest of my behavior with the coordinate of the ball. The conditional event, bounce event, as the name implied, happen when the ball hit the wall, right? So it start, the once behavior is a function that is a predicate behavior, right? So when the behavior is satisfied, then, when the event is satisfied, the behavior is triggered and updated, right? And the update really take the first event, the value, and return the new event. So in this case, I just compose now the velocity ball behavior with the bounce event, okay? I use the accumulator. I have the initial value, 0, 3, because if you remember when you start the game, the ball slightly go left to right, okay? And just start to compose all these the behavior together. Now, the same thing with the y, the velocity for the vertical velocity. And now I update my coordinator. I have my velocity, my position of the ball, behavior, and now I just update it together. Now, in a book, there is this Integrative, which is a conventional name, which is said in a book when you want to apply some extra, some extra functionality, math to change the value of the behavior, right, during the process, right? And here to apply some physics when you do the speed, because there's some gravity when you go up and down and so on. But this is just conventional. This is nothing related. So now I've updated of the coordinator of my ball, x, the same for the y, and that's it. Now I've created all my behavior and just compose them together, right? I create my conditional exit, which is fire when the ball go -1, okay? Which is a predicate, and just switch the behavior, right? So in this case, is a predicate, once behavior. So it started with one behavior, which is game on. Time over? 5 minutes? 1 minute, okay. Yeah, I'm done here. So I have the game state and the conditional exit. And so now I use my execute behavior until it switch, right? So now the game is on and keep playing until the conditional exit event, which is when the ball is -1, fire, and it switches to behavior, which is game over, okay? So I know it's a lot of code to go through in a short time, but really the beauty to me is that it's very simple. You have in your mind your behavior, right? You have a ball, you just, you go x and y, you build your coordinate, your speed, you just compose them, and then you adjust the behavior when the game is on and on and over. And you just compose them. All right, so I show you the boring example about the bank account. I think I can just, we are pretty much over time, so I just conclude here, so I give you the link where you can download the code, right? But really to summarize, to me, FRP is a very exciting topic, right? Especially thinking in the future how all virtual reality is going to, I think, hit the industry and game. I think that is something that you want to take a look. Build your own. It's fun. Trust me. It's a proof of concept. Read the papers. It's not that complex. Like in a couple of weeks, you come out with a very nice solution, and really you're going to start to understand the domain. So that's all I have. Question? And here's the link where you can download the code and the slide. But I think I give you the slide in a second, right? Okay. Any question?
Do we have any questions?
What kind of problems you have met when you start doing F#?
F#? Sorry, the kind of problem?
Yeah, like what kind of maybe strange things you met when you start doing F#?
So I think that the great part about F# is the expressiveness, how you express the domain, right? And then it's a functional language, so there are a lot of positive aspects from there, right? It just works. But really, I think that is succinct. So I come from like 6 years in C#, and then I moved in F# for 4 years, right? And then before that, I had a bit of experience in Haskell, and I like to play with languages in general too. But really, what I like about F# is that You just build your domain, you express your data types, and then you function around your data types. And it really is very productive. You're just able to come out with a prototype or a working program in a very shorter time comparing to other imperative language like Java or C#.
Any more questions? Okay, I think that's it.
Right?
Let's thank our speaker.
Thank you.